Welcome to Chapter 3. We'll be talking about functional groups and intermolecular forces. This slide is a review, and I noticed that the structure did not copy over, which is no problem. I will draw this structure in, and you can add this structure to your notes. HA, that's an A. Okay. HC. So, which is the most acidic proton in the structure below? So hopefully you can see that this is a functional group. I'm not even sure what the pKa value of this aldehyde proton is. It's a functional group and it's not acidic. Okay, so you don't want to pick that. This is an sp3 carbon hydrogen. So hopefully you can see that that pKa is 50. This is an sp carbon hydrogen, so that pKa is going to be 25. And then this HC is an alcohol, OH, right? And that pKa is about 16. So HC is going to be your most acidic proton. Functional groups. Okay, you also have a PDF of just kind of me showing you my thought process of how to determine what a functional group is in your lecture material. And a functional group is a group of atoms, or an atom, but mostly a group of atoms that function. They have similar chemical and physical properties. The physical properties we're going to talk about will be, I call IMF, for intermolecular forces. And these are going to determine boiling points. These are going to determine melting points, which melting points and boiling points kind of go together. If one's increasing, the other one's increasing. There's a few exceptions, but we just don't worry too much about the exceptions. And then solubility. Solubility is it soluble in aqueous, like water, or something like vegetable oil? Vegetable oil is nonpolar solvents. You also see hexanes, ethers, yeah, diethyl ether. I don't know, maybe benzenes. And so a lot of times you want to look and see, do you have a heteroatom? A heteroatom is an atom other than carbon or hydrogen. So mostly you're going to see heteroatoms are oxygen, nitrogen, maybe a halogen like fluorine, chlorine, bromine, iodide, sulfur. So geometry, so physical properties and reactivity. In fact, your whole chapters are based on reactivity according to functional groups. And I'll just do FG for functional groups. So basically, before we get into this, I'm going to just kind of give you an outline what to look for. So the first question, Q1, is there a heteroatom? And if the answer is no, then you're going to have, these are called hydrocarbons. Now hydrocarbons have hydrogen and carbon. You'll see these, there's 4 of them: alkane, alkene, alkyne, and an aromatic. And so an alkane would be like a CH3, CH3. An alkene would be like a double bond. So that would be a CH2, CH2. An alkyne is a triple bond. That'd be like a CH, CH. An aromatic would be like a benzene. And so it's a ring that has alternating double and single bonds. Now, what if you do have a heteroatom? So what if you, and typically we're just going to focus on oxygen or nitrogen, a heteroatom. So what if it's yes? Then you need to ask question number 2. Okay, question number 2 would be, is there a carbonyl? And I have this kind of outlined in your notes. Is there a carbonyl? Okay, so if it's no, the answer is no, then what functional groups do you have? You have, if there's an oxygen, you'll see that's an alcohol. If there is another carbon, that's an ether. So you'll see that oxygen bonds to 2 things, and it likes 2 lone pairs. So it's always going to be bonded to the carbon. So what's over here? If it's a hydrogen, we call it an alcohol. If it's another carbon, it's called an ether. You also have, if it's a 3-membered ether, that's an epoxide. Now, what if it's a nitrogen? So if there's a nitrogen, that's called an amine. Okay, that's an amine. Now, what if there is a carbonyl? What if the answer is yes? So if there's a carbonyl, then you got to say what's bonded on the other side of the carbonyl. So if it's a hydrogen, that's going to be an aldehyde. If it is another carbon, that's going to be a ketone. If it is an oxygen, then oxygen's bonded to 2 things. So now you got to say what's on the other side of the oxygen. If it's a hydrogen, that's a carboxylic acid. If it's another carbon, CH3, then that would be an ester. And what if it's a nitrogen? If it's a nitrogen, that would be an amide. And so those are pretty much the functional groups you want to deal with. So how many carbonyls do we have? 1, 2, 3, 4, 5. So 5 of those. How many here? 1, 2, 3. And then epoxide is an ether. It's just a reactive. And then there's 4 hydrocarbons. So 4 and 5 and 3. I think that's 12. Okay, so the reactivity of functional groups. They determined, sometimes that'll determine if you have electron deficient sites or if you have a nucleophile or a base. So the lone pairs on oxygen will make it a base or a nucleophile. So this is an ether, not an ether. This is, yeah, it's an ether. That's an ether. Here, this is an alkene. And so these would be nucleophiles, right? Because I said that you have a lone pair, double bond, negative charge. Those are nucleophiles. They're showing you that this is deficient on the carbon because there is this dipole. So you always have the carbon skeleton and then you have the functional group. And in this case, these are hydrocarbons, and there's 4 types of hydrocarbons, right? Just hydrogen and carbon. And this is an ethane, it's an alkane. This one, this has a heteroatom. You have an oxygen. There's no carbonyl. So what is the oxygen bonded to? A H. That makes it an alcohol. And because there's 2 carbons, that's ethanol. There's 2 carbons here, ethane. So an alkane, ethane, ethanol, alcohol. So you'll learn naming patterns as well. So they're just showing you that the ethane has only carbon and hydrogen bonds, so no heteroatoms, and they have no reactive sites. These are going to be nonpolar. So we're also going to talk about intermolecular forces, and you want to classify them. So you're going to find that, and this should be review, ionic bonding, electrostatic. So ionic compounds, they have electrostatic interactions. And so these have the highest boiling points and melting points. And they are soluble in water. So that's stuff like lithium chloride, Li plus, Cl minus. What about sodium methoxide? Well, that's a sodium plus. This is an O minus. That's an ionic interaction, intermolecular forces. Okay, well, what about the next one is hydrogen bonding. And you'll find hydrogen bonding. You have to have a hydrogen bonded to either an oxygen, a nitrogen, or a fluorine. So what are your hydrogen bonding compounds? Well, you have carboxylic acids, you have amides, you also have alcohols, and you have amines. And then the third one on the ranking, this is the highest, dipole-dipole. And this is if you have a dipole. So these are carbonyl containing compounds. So that would be a dipole. That would be a ketone. An ether would have a weak dipole-dipole. And then the lowest nonpolar compounds are your hydrocarbons. Because then they would be, these would be van der Waals. Now, if something has hydrogen bonding, it also has dipole-dipole and van der Waals. But we just care about the predominant, the highest ranking intermolecular force. So if a molecule has a hydroxyl group, this is going to have hydrogen bonding. And we'll show you that that'll give it a higher, so if you have something like, let's say methane versus methanol. Okay, so that means this is nonpolar, and this is going to have van der Waals, which we'll just do VDW, van der Waals. This is going to be hydrogen bonding. And you'll see that this has solubility in water, and this also has a higher boiling point and melting point than something with a similar molecular weight. So the properties of ethanol are going to be very different than ethane. So that's, they're talking about ethanol versus ethane. And so, because ethane has van der Waals and ethanol has hydrogen bonding. And all your alcohols are going to have similar reactivities. Chemical reactivities, we can act as a nucleophile. So this is showing you the structure of ethane versus ethanol. And the two lone pairs will, and the hydrogen bonding will cause it to have different properties. The lone pairs will make it have a different chemical reactivity. So this is showing you the classifications that you will be responsible for, and the sooner you learn them, the easier your life's going to be. So here you have 4 different hydrocarbons. You notice there's just hydrogen and carbon. There's no heteroatom. And what's a heteroatom? Either an oxygen or a nitrogen or a sulfur. So here's an alkane, alkene, alkyne, and aromatic. And sometimes it's called a phenyl group. Aliphatic hydrocarbons have 3 subgroups. Alkynes have the triple bond, alkenes have a double bond, alkanes have only single bonds. Aromatic hydrocarbons have this alternating double, single bond. And what you'd find is this, as each one of these are sp2 and they're in a ring. And that's important for resonance structures and unhybridized p orbitals. Okay, what is the functional group highlighted in red in the following molecule, but I don't have a structure on here, do I? Here it is. Okay, so structure did not convert over. I will draw that for you. So what is that functional group highlighted in red? Well, is there a heteroatom? Yes. Is there a carbonyl? Yes. There's your carbonyl. What's bonded to the carbonyl? Hydrogen. That makes it an aldehyde. What is the functional group highlighted in red? Okay, well, is there a heteroatom? Yes. You see there's a nitrogen. Okay, is there a carbonyl? No. So remember that there's just 3 of those, and nitrogen makes it an amine. So do you remember what an alcohol was? That's an alcohol. An amide is a carbonyl containing nitrogen compound. An ester has a carbonyl. I think there's also apps that you can download for your phone. They might actually be free, or they might cost like 99 cents, and you can practice functional groups throughout the day. Okay, a functional group determines all of the following properties of a molecule: bonding and shape. So that's like hybridization. Like you'll find that aldehydes are sp2 carbons, and they're flat, just like a ketone. You'll find that an alcohol is an sp3. So, and these are dipole-dipole. And so where's the dipole located? Towards the carbonyl. These are hydrogen bonding. So ethanol is going to have a higher melting point and higher boiling point than your aldehydes and ketones because of their ranking. And they'll also have a higher solubility in water because water is a polar solvent. Like dissolves like. So if it's nonpolar, it'll dissolve in a nonpolar solvent. If it's a polar solvent, it'll dissolve in a polar compound will dissolve in a polar solvent. This is the intermolecular force, different types of strengths. Physical properties are determined by these intermolecular forces, and that's melting point and boiling point and solubility. Nomenclature, this would be called ethanal for aldehyde. This is called propanone for ketone. And this one is ethanol. Ethanol with an OH for alcohol. So the nomenclature will be different, and their chemical reactivities will be different. We'll talk about aldehydes and how they react. They have different mechanisms. Alcohols have different mechanisms. So intermolecular forces are interactions that exist between molecules. Functional groups determine the type and the strength of these interactions. Ionic and covalent compounds have very different intermolecular interactions. So an ion, it gets like this network. So like every sodium and every chloride will kind of hang out with all the sodiums, and chloride will orient itself And that's just kind of like how that happens. And so salt, salt, sodium chloride, it's a solid at room temperature. And it's very water soluble. So this is those ion interactions. Covalent bonds, hydrogen bonding, that's going to be your highest here for highest melting point, boiling point, and water solubility. And hydrogen bonding has to have a hydrogen bonded to either an oxygen or a nitrogen. So these are your functional groups that have hydrogen bonding. This is an alcohol. This is an amine. Your amides, the nitrogen, the carbonyl containing, and your carboxylic acids. These are all going to be hydrogen bonding. Dipole is going to be second, and these are your ketones, your aldehydes. They have a dipole. And then like your ethers. And van der Waals forces are your hydrocarbons. So those are all van der Waals. These are going to be your lowest melting points, lowest boiling points, and the lowest solubility in water. Van der Waals are also known as London forces. They are weak interactions. They are the only attractive forces present in nonpolar compounds. Your hydrocarbons are nonpolar compounds. All right, so this is showing you kind of a picture of a dipole. And if you get larger surfaces, like bigger molecules, you're going to have more stronger intermolecular forces. So when you get a compound that has a lot of these alkyl chains, then they're going to have higher boiling points and melting points than, say, something with a lower, because you're going to increase the number of van der Waals interactions. So that'll come out into higher melting points and higher boiling points. Polarizability is a measure of the electron cloud. Iodide has a very high, large atoms that are very polarizable, and those are going to have stronger van der Waals intermolecular forces. This is dipole-dipole interaction, so you can see that the electron density pushes towards the oxygen, and then the molecules will orient themselves where the negative will orient themselves with the carbon. You can also draw a resonance structure of this to see where you have your dipole. So here's a resonance structure where that's a positive and a negative. And so that is a dipole, a plus and a minus. Hydrogen bonding, like I said, you got to have a hydrogen atom bonded to either oxygen, nitrogen, or fluorine. So water, this is an example, and you see the dotted line here. That's indicative of hydrogen bonding. Water has 2 hydrogen bonds. So this is some examples of some molecules and their type of intermolecular forces. So here we have butane, and then we also have, they're showing you all these molecules have this, but butane is the only one, the hydrogen carbon, that only has van der Waals. And then if you look at, like I said, if they have any of these, they also have, well, if you have any of these, you also have van der Waals. So look at dipole-dipole. This is an aldehyde. So this is butanal. So you can see that there's the aldehyde, and it has a dipole-dipole. And then you go here, and you can see that you have the alcohol, and the alcohol has the hydrogen bonding. The way I do it is I say the word predominant, and predominant means if it's a hydrogen bond, then you put hydrogen bond. If dipole is the highest, then you say that. Van der Waals for hydrocarbons. Okay, what type of intermolecular force would be predominant for this molecule? Well, let me draw the molecule for you. So in this case, what would it be? Well, you have a hydrogen bonded to a nitrogen, so that's hydrogen bonding. And see, there's predominant, hydrogen bonding. So the predominant one, the one that's going to determine the overall intermolecular forces. So this is an amine, is your functional group on this. Okay, so these are the physical properties that are boiling point. So hopefully you know that boiling point is a temperature at which the liquid molecules go into gas. So the liquid goes to a gas, and so a lot of times you see boiling with the bubbles because the gas molecules are coming from the bottom of the pan, and they get to the surface, and they have this little bubble, and then they get free, and then they become a gas. And so when the molecules go through this process, it requires an increase in temperature. And so it's how close, how strong are these intermolecular forces. So to have a higher boiling point, you have to have stronger intermolecular forces. And so as you can see, hydrogen bonding is the highest, and then van der Waals is the lowest, and in between is the dipole-dipole. And so then you just need to think about some functional groups that undergo hydrogen bonding versus functional groups that do dipole-dipole and van der Waals. This is an example of that. You have pentane. These are similar molecular weights. Okay, molecular weights. So if you added up the molecular weights, you can see that these are very similar. This has no functional group. It's an alkane. So it has van der Waals, and it boils. It goes from a liquid to a gas at 36 degrees. Now this has a dipole-dipole. Okay, and it's actually 40 degrees more, higher. It takes, those are stronger intermolecular forces to overcome in order to go from a liquid to a gas. And then hydrogen bonding, which is your highest, okay, is 118. So that's even 24 plus 18. It's like 42 degrees Celsius more. So that's how strong of energy is represented in the boiling point that molecule has to overcome its attraction for another molecule, because we're talking about intermolecular. Think about interstate. An interstate is like I-71. It goes between the states, between one state to the other state. The intermolecular forces are the interactions between these two. Okay, so here is just showing you the dipole-dipole, and this is a dipole-dipole because there's a polar molecule. The melting point is a lot like the boiling point in the fact that if it has a higher boiling point, it also typically has a higher melting point. We can see some small differences in special cases, and you might have that in these slides, we'll see. But what is melting point? You're going from a solid to a liquid. And you still have to overcome those intermolecular forces, the forces that are holding them together, because you have to separate the molecules from each other when you want to increase the distance. Because remember, a solid is really close together, and then in order for it to go to a liquid, those molecules have to move further apart, and then the gas molecule, they essentially are so far apart they have no interactions with one another. Okay, so for covalent bonds, approximately the same molecular weight, the melting point depends upon the identity of the functional group. So once again, hydrogen bond is going to have the highest, and this is melting point. And then van der Waals will have the lowest melting point, and dipole-dipole will have the intermediate. And so the exception to, or just something to pay attention to, if you have for melting point, because it can be compact, it can make a difference here. This is pretty significant, right? -6 or -160. Let's see what that is. If we subtract 160 minus 17, we're talking 143 degrees Celsius, and they have the same molecular weights. So what's going on here? This one's higher melting point because it's packed more closely. So even though these are van der Waals, and they're still going to be lower than a hydrogen bonder, okay, or a dipole-dipole. We're comparing a van der Waals with a van der Waals. We're comparing two compounds with the same molecular weight. So the only difference here is the packing. This has more packing, so it's going to have 143 degrees Celsius higher melting point. Okay, solubility, like dissolves like. You'll want to memorize that. So if you have a nonpolar solvent, then a nonpolar compound will dissolve in it, and vice versa. So the dissolving process is when you have like a solid and the solvent molecules get in between and separate them, and you see that they're all separated and they're solubilized with the solvent. So like I said, like dissolves like, and let's see. So polar compounds are going to dissolve in polar solvents, and you might want some examples here. Okay, so water would be a polar solvent, and that does hydrogen bonding. So if you have something else that does hydrogen bonding, it's typically going to be soluble. Alcohols also do hydrogen bonding, so ethanol. And ethanol is the active ingredient in beer. So a beer, you know ethanol is soluble in water, because that's kind of essentially what you have. Now, what about a nonpolar compound? A nonpolar will dissolve stuff like carbon tetrachloride. So that's carbon tetrachloride. Hexanes, 1, 2, 3, 4, 5, 6. Okay, hexanes. Gasoline, what is gasoline? Gasoline is octane. So octane, you'll find out is 8. 1, 2, 3, 4, 5, 6, 7, 8. That's octane. And weakly polar solvents is diethyl ether. Even though it has a dipole, it's so weak that it can be considered nonpolar. Soluble of ionic compounds are going to be soluble in water, because, I mean, like lithium chloride, that's a full positive and full minus. Solubility of organic compounds. So here butane is going to be soluble in carbon tetrachloride, which is nonpolar, and it's going to be insoluble in water. Acetone is going to be soluble in both of these. You see they're both because it's polar. And it's kind of nonpolar, so nice little gray area here. Sometimes these are partially soluble in each. Looks like the slides didn't come over. They're just showing you solubility. The reason why is because it can hydrogen bond with water, and that's why it can be soluble in both. It's really how these molecules interact with the solvent. Okay, so ethanol is water soluble and cholesterol is water insoluble. And the reason why, even though it has this OH group, it has so many carbons. So this is nonpolar. And so that's hydrophobic, whereas the polar part becomes hydrophilic. And you get this in that lipid bilayer. This is kind of the lipid bilayer. If you look at the phospholipids and our cell membranes, you have this nonpolar portion. When you think about soaps, and that's very nonpolar. And then you have this carboxylic acid, and this would be a very polar group. So the polars will hang out together, and then these nonpolar functional groups will hang out together. So the nonpolar part of the water is hydrophobic. That means it fears, phobic, it fears hydro, water. Hydrophilic means it loves water. So the polar part will be water soluble. Cholesterol is an example of the hydroxyl group is hydrophilic, whereas the carbon cholesterol is hydrophobic. So that's fearful, and it will repel it. Okay, so here we have a summary of solubility in water versus carbon tetrachloride. That's an example of an organic soluble. Definitely lithium chloride is going to be only soluble in water, insoluble. Alkane is going to be soluble in carbon tetrachloride. It's going to be insoluble in water. Alcohol is going to be soluble, and notice that there's a carbon count. So when you do get more than 5 carbons, then it typically will form one of those polar heads and nonpolar tails. And so other than that, you would say yes, it's okay, soluble. Here we have an alcohol that has 11 carbons. So 11 alkanes. So this is going to be insoluble in water and will be, so the cutoff is the 5 carbons, the alkane. All right, so you need the molecule. So I'm going to draw you the molecule. Which solvent would the following molecule be soluble, miscible? Well, carbon tetrachloride would be your nonpolar, which is nonpolar solvent. And then water would be your polar solvent. So now you've got to look at your molecule and say, is this polar or nonpolar? Well, it is an ether that has a weak dipole, and then it has like 10 to 11 carbons. So I would go with carbon tetrachloride. Like dissolves like, and this nonpolar molecule would be more soluble in the nonpolar solvent. And that wraps up this chapter.